welcome in. So beats and beat frequency. So it's not a very long topic. So when you are studying waves, and in particular when you're studying sound, you might run into this. So what exactly is this concept of beats? And then how do we find the beat frequency? So here's a little bit of a definition within here, and I'll put kind of references back in the description there. So a beat itself is basically a periodic change that you see there of sound intensities that you have that are created by two interfering sound waves. So normally those particular sound waves are very close in phase. Now they're not in phase, but they're very close in phase. Now, when you're first studying this, and I will only focus on the idea that we have kind of two particular sound interfering waves. So you can have more than two, and certainly you can create beats with that, but it gets a little bit more complicated. And when you're just learning it, I think that to grasp it, it's much easier to be able to talk about two, and then you can expand if necessary. So what exactly do we mean, okay, by this definition? All right, and I'll get into beat frequency in just a moment. So if you imagine that you have a sound wave, so let's say, we post up a sound wave. So here is one particular sound wave that you hear. Let's say it's propagating all the way through here. And if you look, okay, at the sound wave which is just below it, so as this propagates the second sound wave, now I purposely have kind of shifted them away from each other so they're not actually on top of each other, at least not yet, okay, so I'll do that. So what we're saying is that if you have one sound wave and then you create another sound wave. Now, if these two sound waves are close enough, okay, you might see a pattern recognition. Now, they don't have to necessarily be close. They can also be out of phase quite a bit. But when they are very close in phase, which these two are, so notice, for instance, this one peaks over here, and if you take a look all the way, well, this one peaks very close by. So now, when you put these on top of each other, they're going to interfere in the real world, right? You don't just separate them out. Okay, what's going to happen is you're going to have either constructive or destructive interferences as you're going through. And when they interfere, what we mean is superposition happens. So we can add them up together. So let's take a look, okay, how we can create a beat. And what do we mean by a beat here when we're saying that we have two sound waves and their periodic change in sound intensity happens? If you just had these sound waves separated on their own, there wouldn't really be any kind of sound periodic changes that you might recognize within here as one goes through and then another one goes through in here. But you will recognize it because of the constructive and destructive interferences that happen. So I'm going to take these two. I'm going to load them up into decimals. So this is what we have. So I've plotted them up together. And now on purpose, I'm going to now interleave them on top of each other. And you're going to see how close that these two actually are. Now, okay, so at first, okay, let's try as best as we can, okay, to see this. So I'm going to now remove right here. So as I go through this, okay, so let me remove that. Let me shift this back out. And now you see these two sound waves on top of each other. And as you can see, at certain points, there's constructive interference. Okay, so that's what you see, okay, definitely as you're progressing through. So for instance, okay, so notice as you're going along here, okay, so there's basically they're on top of each other. Now, as you keep going, there's still constructive interference. Now they're close by, as you can see there. And then they're shifting away further and further apart. And if you get far enough, notice that now all of a sudden, let's say this point right here, okay, that you have, which is 2.5 and 1, and the other one, which is on the opposite side, these two actually create destructive interference. So they basically will cancel each other out. And when they're in the real world, these two sound waves, they're going to superimpose. Now let's see what happens when they superimpose on top of each other. When they superimpose on top of each other, this, okay, is what we obtain. So I'm going to, okay, so now just kind of show you within here. notice the constructive interference, so the huge change up, okay, so over here, over here, over here, okay, as it's going through. But then notice that it slowly starts to decrease all the way down, okay, to 0. And this is what we call a beat. So a beat will be this periodic change between two of these waves intersecting, creating a constructive interference and then a destructive interference. And if I remove the actual two waves and I just leave the actual superposition between them, and I start to zoom in, okay, on this. So if I take this in, okay, and I start zooming in here, so as you will see momentarily, okay, so as you're going through here, so I'm going to zoom out, notice that there is this beat that is created. Now, what do I mean by this beat? What I mean is the following. So this now, from this point, okay, all the way to this point would be called a beat. And all of these, as you continue on, create beats, meaning that we have many of these beats. And notice that they are periodic. One period, second period, third period, and the intensities change from high intensities to basically no intensity. So notice if you had these, the destructive interference would cause that we would hear literally a beat where it goes boom, and then a pause where you almost don't hear anything, and then another beat, okay? This definitely is, of course, intertwined with music, okay, that you have. And these two particular waves, these sound waves, have created these particular beats because of the superposition on top of each other. So again, one of these is called a beat, okay? Many of them are obviously called beats. The intensities of sound are from increasing to decreasing, and they're periodic. So they are continuously, okay, being changing back and forth, and they create this nice looking beat for us. Now, if you want to know what the beat frequency is, well, if these are the beats, okay, and then the frequency, so of course recall what frequency means. Well, frequency means how many cycles we have per second. And if we are looking for beats, well, then that means we can count these up. We can say, all right, well, this beat is equivalent to a 1 cycle. And how many of these beats or how many cycles do we have in here? So as you're going through, so how many of these beats, it's the same thing as in your heart, right? It kind of beats in there, okay, as you're progressing through. Well, these sound waves, okay, so how many beats do we have? How much time has elapsed? And we can then figure out what the beat frequency is. That is the resultant frequency created by the constructed beats that we had from these two particular waves. Now, it turns out that you can actually find what this frequency is. Now, of course, if you have a graph and if we had a timeline, then we can actually find out exactly what this would be. But, okay, the other way that you can find it, and it's very easy to do so, is that the actual frequency for the beat is equivalent to the magnitude of the frequency of the first sound wave minus the frequency of the second sound wave. So if you take these two frequencies, you subtract them, and you take the magnitude, okay, between, that will give you what the frequency is, because of course frequency is greater than 0. It's a positive number. So let's take a look at this from the viewpoint of this example. So here's this example. I've kind of blown it up. I've also now put a timeline on it, and I just want to show you what this would be. So notice that if we had kind of the axis, so notice right there, this is at point 2.5, okay, it's 0. And now how much time passes by for one beat? So I'm going to actually put this one in here, and notice that's 2.5, 7.5. So that's 5 seconds for one cycle or one beat. Well, so if you wanted to find out what the frequency is, well, that's cycles per second. So we would have, okay, in this case, 1 beat, and it took 5 seconds. So 1 over 5 would be the frequency, or simply 0.2. Now, okay, if I bring back, okay, and I show you, and I'm going to remove this, okay, and take these two, okay, and let's take one of them. The frequency of this, now you can convince yourself, okay, by going through this, okay, as well, and seeing it. The frequency of this red wave is actually 2 hertz. And the frequency of the green wave is 2.2 hertz. Now, of course, we can do this individually. We can kind of zoom in here and check what that would be within there. But I'm telling you that, and also on the left-hand side, you can kind of see it, okay, because I put up the frequencies. So therefore, if one is 2 and the other one is 2.2, then of course, by this formula, what are we going to get? Well, 2 minus 2.2, take the absolute value, and of course, this gives you the actual frequency, which is 0.2, which is exactly what we found just by simply looking, okay, at how long it takes per 1 beat. And you can do that with any 2 sound waves. And if they do create this periodic kind of sound intensities from going loud to low, okay, then you've created beats. And beats are nothing else but simply cycles, if you're thinking back of period and frequencies. So that is it for this video. I hope that you found it useful, and now you have a small understanding of what beats are and how to find the beat frequency. Thanks for watching. Bye, everybody.